I'm here, Dr. Dida Murad. Today we will try our best to remain at the topic which is very relevant to biomedical aspects. Genetics evolve genes. Genes we means proteins. It having expressions. It having concentrations. And DNA is transferred to mRNA. And there is a concept of transcription. Transcription we means gene expression. Then we want to connect genetics as cybernetics. Cybernetics is basically an engineering field in which we are designing any controller, in which we are designing any control mechanism, and we are designing any control theory along with some products, in which there is a world of loops, positive loops, negative loops, positive to negative loops. And here's this is known as engineering's control system. Similarly, you can see these phenomena. This is the biological phenomena in which the arrow indicate the intensity to be high. In simple word, I'm saying that activation, the dull shape, this one, inhibition, suppression, like this. There's a concept of closed loop. Our biological system always working in a closed loop. These ideas are control mechanism. It is related with cybernetics. That's why it is related with cybernetics. As a result, we can say cybergenetics is an interdisciplinary area. It involves system biology, synthetic biology, genetic informations, control mechanism. That is known as cybergenetics. Now come to mechanistic data-driven approach. Mechanistic way we means hybrid system. It evolves biology, it evolves chemistry, it evolves machine learning. That is why it is known as mechanistics. It evolves some dynamical behaviors, dynamic problems in the form of ordinary differential equations, in the form of partial differential equation, partial differential equation. Okay? Single system of partial equation, number of partial equations, single ODE equations, number of coupled system of ODE equation in which we have data-driven approaches, mix up of these things, which is related with our mechanistic approach. That can be, it evolves simple in mechanistic driven approaches. It evolves IT, mathematics, as well as in engineering along with data. Data we means machine learning here. Okay. Science we means it evolves biology, chemistry, etc. Now come toward this one this is the game changer. Look here, adaptive control. Adaptive we means it adjusts itself to control mechanism. The mechanisms to be the genetics, the expression levels to be controlled. This is the whole idea about these topics. Now come toward this approach. For example, I'm just mentioning here as a mathematician, I belong to my mathematics community as well as engineering community based on my PhD work in computational science and engineering. We know about ordinary differential equations. We know about neural features. Look here, neural features. Neural feature means AI, neuron systems, in which we have deep learning evolved. Whenever we are using adaptive controllers, it is adaptive control is engineering approach. We can mitigate the biasness. Look here, the bias reduction. What's mean by the bias reductions? I want to clear to you the bias reduction here. For example, this is the system here. This is the reference value. For example, this is the upper value. This is the reference value. We are here. We want to reduce the difference between the main points and the reference value we are set. We want to reduce this one. Whenever we want to reduce this one, we are making the error reduce. Whenever we are making the error reduce, we are making thing precise. We are making thing precise. Okay. That is why it is the attributes and characteristics of adaptive control system. It can reduce the biasness as 63% in our today's session. Then our adaptive control or adaptive control mechanisms mitigate and faster settling. Look here, this is the attributes or machine. It speed up your, it make this 75%. It is not available with any traditional controllers. Traditional controller we will discuss about PID controller, sliding mode controller, integral sliding mode controller, double integral sliding mode controllers, and some advanced mode control. But the adaptive is something different, having high attributes because it having faster settling point of 75%. I am considering here according to my lab-based work, which is 75%. And there is an idea of overshooting. What's it mean by overshooting? Overshooting means abruptly increase, abruptly change. This is known as overshooting. In engineering point of view, for example, we have any gene expression. It is high expressed. It having high amplitudes. For example, in traditional adaptive controller, in traditional controllers, for example, we have PID, sliding mode controller. We have overshootings we are facing. But the attribute of adaptive controllers, it means it can reduce the overshooting of these ideas. It can reduce the ideas of overshootings. These are main three aspects we will observe in our adaptive control system. Okay. Now come toward here. I'm just giving you the roadmap about our research strategy. What our strategy and what we are going to research here. In 2026, quarter first and quarter second. For example, today we are starting our research. This is our quarter first. After 3 months, after 6 months, it is considered to be Q1 and Q2. We will design, and we are already designed mechanistic neural fusions here. This is our first step for 6 months. Then we will integrate a wet lab integration. Basically, in wet lab integration, wet lab is related with your lab-based work, in which you are considering FPGA. You can see as FPGA. What FPGA indicate? Field Programmable Gate Array. It is basically hardware chips. It is known as integrated circuit. It is known as silicon chips. Here in this purpose, in wet lab, we are designing. It is used as a real-time controller. FGPA is a real-time controller. It processes signal from our biological system. The biological system is known as, for example, sensor in microfluidics, because our engineers know about microfluidics. Is this the sign and text of manipulating, controlling, and tiny amounts on fluids here. And this is having the attributes. FPGA have the attributes as 20K hertz. 20 hertz means 20,000 per second. It having the capacity to work as a controller, because it is related with our wet lab. We are working on it in 2026 in Q4. These are our aspects in 2026 for your roadmap. Then come toward 2027. In 2027, we are developing our neural operators. Neural operator advanced AI models, they learn how entire system behave, not just signal value. For example, we have parameters in the form of disturbance in the parameters. We have variables, and we have the concept of temporal system. Temporal, for example, these the expression values, the change in the concentration of proteins are considered to spatial temporal phenomena, because it evolves space and times. It evolved the change in the time, the change in the expression values. We are developing in our neural operators. These are our roadmaps that we are going to touch in 2016, and we are welcoming here to come and discuss your problem here if you are interested here. Now come towards some mathematical aspects. My communities as a mathematician as well engineer about advanced scientific machine learning. I'm taking time here. I'm giving the time here on ordinary differential equation system, because so that we can move towards onwards. I want to make it clear. For example, what X indicate? X indicate the transcription factor, the transcription of the gene, the concentration of the gene. It is considered to be 1 ODE. It may be 2 ODE, 3 ODE, 4 ODE, 5 ODE. In my system, in my PhD, you can see this system. For example, I'm showing that system. This is the system you can see here. In my PhD first paper, what you can see this system. It having 198 ODE system, you can see here. It evolved positive loop, negative loop, you can see here. Upward signal and down signal like this concept. Let me to come again. This is the ODE system. For example, this is X. This is the transcription factor. Simple word. The change in expression with time. Expression we means concentration of protein, concentration of gene. Gene we means protein. Look here. We have alpha term, alpha T. It is basically indicate the growth factor. Something is going to increase, alpha T. It evolved the beta. Something is going to decrease because in the form of minus, it is multiplied with X. The only things, the first alpha T and beta with X, it develop your mechanistic approach. Okay, this is our ODE system. It evolved the mechanistic approach. Now I'm not coming to a neural, and I later on discuss these two. But keep it to mind. Here I want to discuss in comprehensive way is you can use 4 mechanism techniques here, 3 mechanism techniques. The first mechanism techniques is you can join 2 proteins in the form of using mass action law. You can use as Mechanistic law here. You can use here Hill function law. You can note these things. You can use here as a biologist, as a chemist, as engineers, keep it to your mind. Here I would say that you can use here the techniques, the biological techniques, the chemistry techniques, which are known as law of mass action here. You can use Mechanistic law here, which is the chemistry techniques. Similarly, you can use Hill's techniques, Hill function develop here, because Hill functions is applicable in proliferation problem. Proliferation means abruptly change, abruptly high change, high reduce. Those things, it is highly increase, that is related with your proliferation problem. Those it is related with high decrease, it is related with proliferation problem. At that respect, you are using as here as Hill function here. Now I am coming toward here. Look here. Neural arguments. This is the AI techniques we are using. This is known as scientific machine learning techniques. We are developing the function here, r theta, which depend on x and t. Which depend on x and t, the space. X is considered to be the space and t is considered to be the time of t. That it is basically the control input function. Engineer know about it. Engineer apply it. But here I would say that it is basically the dosing phenomena of the drug. For example, we are picking, this is our biological system. This is our biological system. We are building some external modulator. External modulator we means the drug outside. It can touch its. It means in order we have to control the dosing phenomena of these drugs inside our body. Whenever we are controlling this thing inside our body, which is known as the controller, U of t, this is the control input function. We have to develop, this is the conference papers. Our engineers and myself are publishing their things. I myself is published their things in biological aspects related with integral sliding mode control along with machine learnings, deep learnings. I have touched their things as well. This is the techniques. What U of t indicate? U of t can be mathematically defined here. It is, look here, Kp. What Kp indicates? Kp basically indicates the gain factor. Those who are engineers are already know about the gain. We are using for, in my paper, I use C1, C2, C3. Here I am just showing it as Kp. These are the gain. We can tune the gain. Because in PID controller, main session is, we want to compare our adaptive controller with PID controller. So that you can differentiate PID controller and adaptive controller and SMCs like this. Okay. This is the controller compensator. What basically the neural compensator indicates? Neural compensator basically indicate the AI compensator, artificial intelligence compensators, which is in the form of R theta W1 10H hyperbole 10H W2X plus B. You can see these are W1 and W2 are weights. This is the variable X. This is the bias. I want to demo on it, please. Look here. This is the demo I developed for you in my demo calculator. R equal to W1 theta H W2 X2. You can change W1 X according to your desire. Okay, according to your desire. Depend on your machine learnings, how you are adjusting these things. Okay. In your models, you can use the log of H as well as sine of H. Why we are using in our system? Because we have to bring some novelty in our ODE system, ordinary differential equation system. Whenever you want to publish things, you must the model to be novel. In order to bring the novelty in the system, you must make your neural compensator as strong as much as possible. You have to develop the novel idea here by adjusting W1, W2 here, W1 and W2 here. You can see here, these are the adjuster. And what is the attributes of B? It's only translate the problem. What is the attributes of W2? It's only change the problem, the fluctuation, the amplitude of the graph. Look here, the amplitude of the graph, it leading toward here. And you must play, W1 is very important. Then W2 is important. Then B1 is indicators is important. We are usually using these concepts in our deep learning about neuron. You know about the neuron. Okay. I also comments here is about supervised learning models, which are known as gradient descendant. Look here, the gradient descendant. This one is the gradient descendant. If supervised learning models, in which we have the gradient concept. In the first, we have the high error. Whenever it's going to increase, the iterations is going to increase, the error is going to decrease, the loss function is going to decrease. That is why the neural compensator is related with your loss your loss function. Loss function is basically the error, the residuals and errors. Okay. That's why this is neural compensator is the main game changers. I'm recommended here that you must evolve inside your ODE system at neural compensators so that you bring in your research as you make your model is strong so that you can easily publish their things. Now come to toward another aspect which is known as Lyapunov as stability. We know about, for example, every engineers and mathematician know about the Lyapunov stability function. We have to design our Lyapunov ODE systems, and we have to go toward the stability conditions. We have to develop these things here. Okay. Now come toward my demo. I want to come toward my demo about the PID controller. Look here, PID controller, proportional integral differentiation controller. This is the traditional controller. It is available in Simulink. Reference value means the set value. These are the X to indicate protein concentration. I'm using my PID controller. Okay. I'm using the PID controller as I'm increasing it. Look here. This is basically mechanistic model. It is going to increase by help of alpha. We are increasing. This is not, it means I'm adjusting it. This is the degradation factor. Look here. Based, no, I'm sorry. This one. Yes, degradation. Degradation means the decay factor. I want to increase the decay factor so that it can. Whenever I increase the decay factor, look here. What is the decay factor in my mathematics? You can see here in the form of minus. Something is going to reduce. Here you can see it as alpha t. Something is going to increase. At their respect, you can see my simulator as whenever I increasing the growth factor, it's going to increase. Whenever I'm decreasing it, it's going to decreasing factor. When I'm increasing it, it could go to, because it is a degradation factor in biological phenomena. Now this one is my gain. This is important. Please keep it to your mind. I am taking it as, look here, this is just a PID control. Look here, the gain factor, which are using KP here in controller, KP as ET. Basically, ET indicate the error term. What the error term indicate? The error term indicates the change in the expression value and the reference value. The gap between them is known as the error term. We want to reduce their error term. For example, this is the set point, and this is the gap between these two curves. This is the first curve, and this is the second curve. This is the set points, and the distinction between these two is known as an error term. Now, in PID controller, we have to adjust. Look here, we are adjusting our gain. We can adjust our gain in order to reduce the error so that it can further tracking to it. Look here. Here the KP is very low. Look here, the gain is low. Now I am going to increase the gain here. It leads toward the reference points. Okay. Now this one is the set point. I already set it as 5. Look here, this is the set point. It is basically set point. Okay. This is known as the PID controllers. Along with PID controller, you can use a sliding mode controllers. You can go toward my publication first. and publication second. And our engineers who are already published work in energy sector as well as health sectors, you can go and understand that PID control SMCs and advanced more controllers. But they are also use adaptive controller as well as. Okay, this one. Now come toward this one. This is the capacity of these controllers, which is known as adaptive as a scientific machine learning controller. It means this is the reference points. Look here, this is the adaptive. But keep it in your mind. It may be offline, it may be online. You can touch your machines to the system as online as well as offline. Whenever you are touching the machines to online, it needs some data to be trained from outside environment. Whenever you come toward inside environment and offline, you must have the data inside your systems so that it can train. Look here, the capacity KP, the gain, it is going to change. KI, it's also the gains related. Okay, look toward the neural weights, the AI, the weights, it is going to adjust itself. W1 and W2, and how it is tracking toward the reference value. This is the spirit of your adaptive controller along with your machine learning. That's why it's tracking toward its level. Now, according to my analysis, I'm going to discuss about and what are the performance of these two controllers, the very traditional controllers and PID controllers, and very mechanistic data-driven as scientific machine learning controllers. In PID controllers, you optimize gains. Yes, there's a need of optimize gains by hand. Okay. Integral absolute error. Okay. Integral absolute error. Look here, the error of PID controller, which is 24.1. Here it is 6.9. This is the main comparison. Here you can see the setting point of 2% after 15.4 seconds in PID. But here you can see as it is just 3.8 seconds. Here it is 15.4 seconds. Look toward the setting value and 75 reduction rate in PID in mechanistic data-driven control. This is the spirit of your adaptive controller. It can easily reduce and setting the values. This is the third attribute. Look toward the overshooting. The overshooting is not shown here. But keep it in mind, in PID controller, in SMC, you will face overshooting, but adaptive, you can mitigate, you can reduce your overshooting. Look here, it is 19.22%, it may be increased, but here it is considered to be 2.1 shooting. Okay. What is the robustness? It is very poor. PID is very poor. It is automated. Look here, automated recovery under drift. It's having the capacity of automated recovery. This is the spirit of your mechanistic data-driven adaptive controller. Okay. Then you have, look here, the noise level. What do you mean the noise level? For example, you have the data. It is very scared. It have a high scared. You have the data. It have a high scares. It have outliers. For example, this is the line. Look here. This is the line. Some data are very close to line. It means it's having no noise as compared to the data which is very far away their line. For example, some data are very here, up and down. These are considered the outliers. At their respect, every problem which are realistic in nature are always noisy. PID control is very sensitive because it works as a moderate. Yes, it having attributes. It is right, but it's not the good things. You must deploy your PID controller and very advanced controller along with your PID so that you compare the controllers. Okay, you can see here noise sensitivity, which is low, because whenever there is a change in the data, there is a noise in the data, there are outliers in the data. It never interrupt. It never in effect your adaptive machine learning controllers. These are our future direction. We are going to touch this one in physics informed neural network operators. In later stage, we will evolve our PID controller here as well as our engineers. I myself are working in different projects which these are going on, and we also bring some real-time FGP with hundreds hertz here. But because in this project we are using what is the FPG level? The FPG level speed level is 20 kHz. In 226 we are going to evolve as wet lab integration. But here we are going to discuss about, look here, this is this one. In 2016, in extension works, in AI-driven manufacturing and multi-scale controller, we are going to increase our FPGA as a 100K hertz. You know FPGA, because we have CPU system, GPU systems. It means that are FPGA is very highly proficient. Okay, whenever we come FPGA systems in our more advanced system, it become very high advanced techniques. It means these are our future direction I'm just giving you. Now I'm going to come toward your queries. If you want to ask any queries from me, you can ask anything from me here.